Welcome you all. Today's topic horn antennas. Myself, Dr. Prasanna, professor in YC Engineering College, Nagpur. Horn antenna is nothing but a hollow metallic pipe, and its side walls may be flared E sectoral horn or S sectoral horn, or we can flare both the side. Horn antenna is widely used is as a feed element for the large radio astronomy, satellite tracking, and communications dishes. Its advantages: it has a moderate directivity, low standing wave ratio, broad bandwidth, simple construction, and easy feeding. See, this is the pictorial view of a horn antenna. You try to understand how it looks and what is exactly the meaning of horn antenna. See, here is a waveguide, and these are the portion we have to make it flare so that it acts as an antenna. So it consists of a waveguide. This is a waveguide, and impedance of a waveguide inside is around 50 ohm, whereas impedance outside the waveguide is around 377 ohms. That is called a free space impedance. And if you use as an antenna this waveguide, you cannot, because when the wave is propagating along the z-axis, that time when it appears in the opponent, it will be reflect back because of the big difference between the impedance of 50 ohm as a 377 ohm. So to make the waveguide as an antenna, we have to flare might be a B dimension, might be a dimension, or both the dimension. So if you use X band, it is known as a WR90, and range of frequency is 8.2 to 12.4 gigahertz. Corresponding broader dimension is 0.9 inch and narrow dimension is 0.4 inch. This is 0.4, this is 0.9 inch. Cutoff wavelength is nothing but lambda c is equal to 2 times a, that is 2 into 0.9 is the dimension, and this is for the centimeter conversion 4.572. Corresponding frequency is 6.56 gigahertz, means 10 to the power plus 9. So this horn antenna at the beginning invented by the Indian researcher, that is Jagdish Chandra Bose, in 1897. It is pioneering experiments with the microwaves. But first modern antenna was developed in 1938. Wilmer Burrow and G.C. Southworth. Advantage of this horn antenna is there is no resonant element, and therefore the bandwidth on which it operates, it's a large frequency, that is the large bandwidth. It may be a 10 times to 1, or it may be a 20 times to 1. It means lowest frequency is 1 gigahertz, that time the highest frequency should be a 20 gigahertz. So it's the input impedance slowly varying over the wide range of frequency, low voltage standing wave ratio over the bandwidth, and gain is around 25 dBi. So electromagnetic horn can take many different forms, four of the which shown in the figure. These are the four different forms of the horn antennas. This is called the E-plane horn antenna, H-plane horn antenna, this is pyramidal horn antenna, and this is a conical horn antenna. This is E-plane. This is broader dimension, this is the smaller dimension. And this is, we make the E-plane has to be a flare, and therefore E-plane is a Y direction to be a flare, and therefore this is B, Y dimension, there is a B, so B, this is the B side, and this is called the A side. It remains same as small a. Electric field in this direction, and if you see the electric field is maximum at the center and minimum towards the edges. Now this is for the H-plane sectoral horn. This is H-plane has to be a flare out, that is H-plane means we can say A dimension wall to be a flare out. This is A and this one is B. B is nothing but small v, and this is pyramidal where both E and H plane has to be a flare out, so we can get the pyramidal horn antenna, and if we use a circular cylindrical waveguide, we can get the circular horn antenna or conical horn antenna. These are the pictorial views of different shapes of antennas. So pyramidal horn antenna is the most popularly used horn antenna, where all the four sides of the rectangular waveguide has to be a flare out. It uses the linearly polarized radio waves, and E-plane sectoral horn, where E field is to be a flare out, which that is y-axis. H-plane sectoral horn, where magnetic field or H field, which is along the x-axis, has to be a flare out. This is the front view of a E-sectoral horn. See, this is, we can say, the big aperture, that is called the capital B. Half of that is B by 2, B by 2. This is theta, half of that theta by 2. L is the radius of this curve, and this is L plus del E. Del E is a phase error. This term introduces because of the phase error, and this is small b. If you just take a half of portion of upper one, L b by 2, and this is L plus del E, and this is the equation. That is, we know that electric field present along the y direction only, and therefore this is E1 cos pi by a x dash, and this is the phase distribution. If you put the value of x dash is equal to a 0, that is, you will get the cos 0, that is the maximum, which is at the center. When x is equal to a by 2, you will get a cos pi by 2, nothing but 0. So at the edges you will get the 0. If you solve this particular Pythagoras theorem, that is this square, that is L plus del E square is equal to L square plus b by 2 square, and if you solve it, equate it, you will get this particular equation, that is called the length for the E sectoral horn is b square upon 8 del E, whereas length for the H sectoral horn is a square upon 8 del H. So this is the solution. We use this Pythagoras theorem. L square get cancelled out, and finally del E is the incremental length, and square of that is further small, so it can be neglected. Finally you will get this. So LE and LH are the slant length for E field and the H field direction. Del E and del H is the E plane flaring difference and H plane flaring difference. Alpha E, we can also call it as a B, is the width of the aperture. Alpha H, or we can say called A, the width of the aperture in H field. This is for E field. Efficiency antenna, that is eta. D is the diameter of a cylindrical horn. L is the slant length. So E-plane sectoral horn, the maximum phase error del max, how much would be? The maximum directivity formula is B is equal to under root of twice lambda LE, where LE is nothing but L plus del E, and corresponding phase when y dash is equal to B1 by 2, then we can, if you calculate, you will get this B square upon 8 lambda LE. If you put the values of that, you will get 1 by 4, and we put 1 by 4 in this S value, replace, you will get 90 degree del max, which is quite large, not recommended. 45 degrees is enough. This is the directivity versus the aperture, that is the B dimension. If you observe that as the aperture go on, B dimension go on increasing, directivity increases. Okay, but after a certain limit, it starts decreasing everywhere. This is that is 100 times lambda. This is 6 times lambda. Higher the we can say 100 times lambda, larger the size of antenna, and this is the smallest size of the antenna, we can say. So it is as you observe that gain in directivity increases linearly up to certain limit, and we have to choose the dimensions accordingly. Like that is the value of 0.225 times lambda, and that del H is equal to 0.4 times lambda. This is a sectoral horn antenna shown here. This is the formula, and if you take x is equal to 1 by 2, once again the maximum field here. This is A dimension, capital A, or we can say A1. This is B is same as this, or this is capital B. It is here the maximum directivity for each sectoral horn is A1, or we can say capital A, under root of 3 lambda rho 2. Now earlier it was 2 lambda rho 1, it is 3 lambda rho 2. Remember, rho is the, that is equal to LH. Then maximum phase error, you can, if you solve it, okay, this is A1 square upon 8 lambda rho 2, and it becomes 135. It is also quite large, it should not be use small values. This is a pyramidal horn antenna where both the plane, the E plane and H plane, has to be a flare out. These are the front view of that is the E plane and H plane, where PE is equal to PH, okay, and because of both the plane has to be flared simultaneously. These are the pyramidal horn antenna. These are the further solution of this. These are two equations that comes from the E sectoral and H sectoral horn antenna. and this is rho 2 is equal to pH, rho 1 is equal to PE. Rho we can call as the LE, and this is LE, and this is LH. This is conical horn antenna, and in this conical horn antenna, that is the S is equal to dm square upon 8 lambda L, that is maximum phase deviation in the lambda, and gain is equal to under root of 3 lambda L, and del max if you calculate is equal to around 135, which is also quite large. So while designing the H parameter horn antennas, we have to consider the E plane horn and the H plane horn. So half power beamwidth is equal to 56 degree upon A lambda. Full first null beamwidth is equal to 115 degree upon A lambda, where A lambda is nothing but A by lambda, and del E is equal to 0.25 times lambda. Means del E, that this is the incremental length for the E sectoral horn antenna, it should be less than equal to 0.25 times lambda. Similarly, for half power beamwidth for H plane horn antenna, 67 degree upon B lambda. First null beamwidth is 172 degree upon B lambda. B lambda is equal to B upon lambda. Del H is equal to 0.4 times lambda, less than equal to. Means while designing, these two parameters are very important, del H and del E. If you choose beyond this particular threshold value, then there is a large phase error, and then antenna will not be work, or we can say directivity start decreasing. This is the gain of a horn antenna. G is equal to 4 pi AE upon lambda square into eta is the efficiency of antenna efficiency. AE is the aperture area, that is we can say large dimension A multiplied by large dimension B. Gain of the conical horn antenna, pi d upon lambda whole square into eta, where d is the diameter of a conical horn. These are the formula we can find out the gain of this. This is a conical horn antenna. And now there is a corrugated horn antenna. It was invented in 1964. The K realizes the grooves on the walls of the horn antenna are present. That is, the boundary conditions of all the four walls would be eliminated. The spurious diffraction at the edges of the aperture. Square aperture would be lead to an almost rotationally symmetric pattern with equal E and H plane beamwidth. So this is reduce the that is the spillover efficiency and cross polarization losses. Efficiency also 50 to 60% without the corrugated horn. It becomes now, after using it, becomes 75 to 80%. Of course, the structure in the back lobe region is strongly influenced by the diffractions from the edges, especially from those that perpendicular to the E field and H field. This is the picture view, that is corrugated horn, and this is the E plane view, that is B1 by 2, B1 by 2. This is B and this is A1, or capital B and capital A, and these are the grooves to be drawn. And this is finally, we can say that corrugated can also be placed in conical horn forming a conical corrugated horn, also referred as a scalar horn. Applications of this antenna is macro engineering as a feed element for the parabolic reflector, radio astronomy, satellite tracking, short range radar system, micro radiometers, communication dishes such as the radar guns and the automatic door openers. These are all applications we use of a horn antenna in various places in micro engineering. This is the most popularly used antenna because it gives a satisfactory performance parameters. So with hope you are getting detail about the horn antenna. Hope you understand it. If you have any doubt, you can send me a mail, and if you like it, please share this video with your friends. Thanks a lot.